Good morning. And thank you all for joining us first thing this morning for this very important and very exciting announcement and program. I am Michelle Wheatley, Vice Chancellor and Provost of Syracuse University. Before we begin, I would like to acknowledge, with respect, the Onondaga Nation, the indigenous people on whose ancestral lands Syracuse University now stands. On behalf of Syracuse University, I would like to give a warm welcome to all of our special guests, including a number of Syracuse University trustees. We're also very glad to be joined by a number of classes from regional high schools. I hope I have them all listed correctly: Henninger, Palmyra and Macedon, and Weedsport. And there is one individual we'd like to stand and be recognized. We're very honored to be joined by Dr. Josh Goldberg. Dr. Goldberg, might you please stand? Dr. Josh Goldberg is Emeritus Professor of Physics, and 60 years ago he organized the meeting that established the field of gravitational wave detection. So I hope you're happy with what you're seeing today, Dr. Greenberg. I can't tell you how thrilled I am to be part of this historic day in the life of the university and in the lives of all of us who value knowledge and discovery. I suspect most of you already know that what you're about to hear involves a truly revolutionary scientific breakthrough. It's a discovery that once again involves our own physicists from the College of Arts and Sciences. That's right, the LIGO team from the physics department has done it again, and you will hear all about it very shortly. We have a full agenda today. You will hear from a few of the LIGO physicists themselves, as well as from Chancellor Syverud and the Dean of Arts and Sciences, Dr. Karen Rouland. But right now, I ask that you all turn your attention to the screen where a live press conference is just getting underway at the National Press Club in Washington, D.C. Let's listen in.
There is, of course, another event we were keen to detect. Today, we're thrilled to announce that scientists have detected gravitational waves coming from the collision of two neutron stars, the smallest and densest stars. This event occurred 130 million light years from Earth in a galaxy far away. The LIGO detectors first picked up the signal. When Virgo did not see a signal of similar magnitude, it was clear the event was close to one of Virgo's blind spots. This enabled scientists to localize the potential origin of the signal more precisely, allowing ground and space-based telescopes, some 70 in all, to turn their attention there as well. What makes this discovery even more exciting is that scientists were also able to detect light, electromagnetic waves, from the collision. The very same cosmic event seen for the first time through multiple messengers, gravitational waves and electromagnetic waves. As an astrophysicist, and someone whose passion for physics was first ignited by a television program on neutron stars, it's especially exciting for me to report on this rare event. Already it is transforming our understanding of the universe with a fresh narrative of the physics of stars in their death throes. The scientists who conceived of building LIGO and were primary drivers, Kip Thorne and Barry Barish of Caltech and Rainer Weiss of MIT, are receiving the 2017 Nobel Prize in Physics. Their vision and perseverance and NSF support made this discovery possible. This is what NSF does. We invest in high-risk, high-reward research that produces the discoveries that transform our world and advance the frontiers of knowledge. The benefits of these discoveries are not confined to the scientific community, but extend throughout the world, as discoveries from basic research coupled with novel engineering often do. Today's announcement should excite the scientists and non-scientists. It's a measure of what is possible when we have the courage to push beyond the limits of our knowledge and pursue answers to big questions. At this point, let me turn the program over to Dr. David Reitze. When we first announced the first gravitational wave discovery a year ago, David captured the excitement of the moment when he declared, "We did it." Well, Dave, we did it again.
Thank you, Dr. Cordova. Good morning, ladies and gentlemen. We have, for the first time, seen both gravitational waves and light from the collision of two dense dead stars called neutron stars. However, to do it this time, we joined forces with thousands of astronomers and many, many observatories. So we did it again, but this time we all did it. Let me start by telling you what we saw. The LIGO-Virgo network discovered two neutron stars colliding together. So LIGO is the LIGO Hanford and Livingston Observatory here in the United States. Virgo just started operating in August of this year, and we saw a signal at 8:41 a.m. Eastern Time on August 17th. The signal was much different from the black holes that we had detected before. It was much longer. And we analyzed this signal, and what we found was that it was a neutron star, approximately 1.6 solar masses, colliding with a second neutron star, approximately 1.1 solar masses, about 130 million years ago, 30 million light years away. So this graphic that you're seeing here is just the brief second where they collided. Now, this is a source that we always thought we would saw. Neutron star systems, binary neutron star systems have been predicted for decades, and we knew that we would see them. For me, what makes this event so amazing is what came next. The emission of light across the entire electromagnetic spectrum, revealed to us by a campaign involving 70 observatories, including 7 space-based observatories and every continent on the planet. So if you look at the graphic carefully that I'm showing, you'll even see there's a dot in Antarctica. So this is quite dramatic. This is an amazing, amazing discovery. And it was made possible by the fact that LIGO and Virgo, operating together, can identify the place in the sky where this event came from. It came from the southern hemisphere. It came from the Hydra constellation. So let me tell you a little bit about neutron stars. Neutron stars are very different from black holes. Now, they're produced from supernova, the explosion of massive stars. They're approximately 1 to 2 times the mass of the star. However, they're made up of pure neutrons. And the density of the neutrons in the neutron star is much, much greater than atomic nuclei, actually about a factor of 3 times greater. So consequently, they're very compact. Neutron stars are about 20 to 25 kilometers in diameter, and you can see in this graphic that I'm showing you the Bay Area in San Francisco. That peninsula is San Francisco. So what you're seeing there, to get a sense of this, is 1.5, 1.6 solar masses packed into a very, very compact region. So, all right, what does this really tell us? Well, astronomers have thought for a long time that the collisions of these neutron stars produce heavy elements, and there's been hints of that in other astronomical observations. But this result provides definitive evidence for the first time that elements such as platinum, gold, uranium are actually produced in these collisions. So I'm going to take out this is my great-grandfather's gold watch. It's about 100 years old. The gold in this watch was very likely produced in the collision of 2 neutron stars approximately billions of years ago. We don't know exactly when. So this is really an amazing discovery. You're going to hear today from the physicists and astronomers who participated in this remarkable discovery. In fact, the scientific story is so rich that it takes 2 panels to tell it. So you're going to hear from 2 different panels today. For me, the story is actually...
Before we go any further, will you all join me in congratulating our physicists from the College of Arts and Sciences who were an important part of this discovery? Dr. Duncan Brown, the Charles Brightman Endowed Professor of Physics, Dr. Peter Solson, the Martin A. Pomerantz Professor of Physics, and Dr. Stefan Ballmer, an Associate Professor of Physics. Congratulations to you all. Well done. You will hear more from Duncan and Stefan shortly. Peter is in Washington, D.C. at the National Press Conference. Research and discovery have always been an important part of the Syracuse University experience. Under Chancellor Syverud, our commitment to scholarship with global impact has become stronger and more robust than ever. Today's discovery exemplifies that commitment, and it reaffirms Syracuse University's role as a world-class research university. Please join me now in welcoming Chancellor Syverud.
Good morning, everyone. I know what you want to hear is this incredible panel. I just want to join in welcoming you to a golden day of awe and wonder here and around the world. This is a happy day for our gravitational waves team, for our physics department, for our College of Arts and Sciences, and for the whole of Syracuse University, and really for everyone on Earth who cares about discovery and the advance of human knowledge. I'm proud to be with you at Syracuse University, at this global research university, to join in honoring the faculty and the staff and the students who've contributed so much to this great discovery. They have brought distinction to themselves and to their university, and we really all are grateful. I thank the physicists in the College of Arts and Sciences, in particular Professors Peter Solson, Duncan Brown, and Stefan Ballmer. I thank the members of the Physics Department's Gravitational Waves Research Group, more than 24 students, research staff, and faculty who come here from around the world. Of the more than 50 colleges and universities around the world who have partnered in this gravitational waves work, Syracuse University is very proud to have one of the largest, longest standing, most diverse, and most impactful. I thank the members of the staff in Information Technology Services at Syracuse University for helping with computing power and infrastructure support for the worldwide team. I thank the leaders of our College of Arts and Sciences, both in the physics department and in the dean's office. They had the foresight and the patience to support gravitational waves research for 60 years. Last year, on February 11th, 2016, we were in this same space in Goldstein Auditorium in the Shine Student Center to participate in the worldwide announcement that the existence of gravitational waves had been confirmed for the first time, and confirmed by LIGO measuring the collision of two black holes. Students, faculty, and staff from Syracuse played major roles in that now Nobel Prize-winning discovery. Students, faculty, and staff presented here on February 11th, 2016, and the broadcast was watched all over the world. They answered our questions that day, and I remember the questions well. One of them was this: now that you have discovered for the first time in millennia a totally new scientific way to observe the universe, what do you expect to discover? Another question, and I think it was from Professor Sam Gorovitz, was, I think, this: what are the implications for this discovery for fields other than physics? On February 11th, 2016, Professor Duncan Brown answered those questions, and what he basically said was this: we don't know what gravitational waves will enable us to observe, but we know it will be full of wonders, and we know it will have implications way beyond physics and astronomy. Today, 20 months later, on October 16th, 2017, Duncan Brown has been proved right. Today is a golden moment for many sciences, including chemistry, earth sciences, materials science, and engineering. It is also a golden moment for the pursuit of knowledge and wonder at this great university, Syracuse University, and I really thank everybody who made it happen. Thank you.
Thank you, Chancellor. Our next speaker will be Karen Rouland, Dean of the College of Arts and Sciences and a distinguished professor of chemistry. The College of Arts and Sciences is home to the university's Department of Physics and to the physicists who are part of the LIGO scientific collaboration. Dean Rouland.
Today is a great day for Syracuse University and the College of Arts and Sciences. For decades, our physicists have been working on this project in labs around the globe. Much of their work has involved trial and error, and until recently has happened with little or no fanfare. Today, we rectify the latter. The detection of gravitational waves from colliding neutron stars marks a new chapter in science history. More than 1 billion years in the making, it helps us answer important questions. What is the universe made of? How did life begin? How do we fit into the universe? And how does the universe fit within us? Donald Kennedy, a Syracuse biologist who became president of Stanford, has said that science is full of puzzles which drive research. They help us identify what we know and what we do not know. We began wrestling with these puzzles in the 1940s when an assistant of Einstein's named Peter Bergman founded the nation's first general relativity research group at Syracuse. He and other star faculty members, including Joshua Goldberg, who supported the first international conference on general relativity, laid the groundwork for what we celebrate today. It was with the arrival of Peter Solson, who quite literally wrote the book on gravitational wave detectors, that Syracuse turned a corner in the 1990s. Peter co-founded the LIGO scientific collaboration and served as its first spokesperson. He was among the first people to propose that neutron star binaries are a dominant source of gravitational waves. Peter joined forces with Duncan Brown and Stefan Ballmer, and the fate of gravitational wave astronomy was sealed. Their contributions to LIGO's Nobel Prize-winning research have pushed the boundaries of science and technology in ways unimaginable. This work is not possible without the support of many, many people. First of all, the members of the physics department and their families. The leaders of Syracuse University, past and present, including Chancellor Ken Sirwood, Provost Michelle Wheatley, and Vice President of Research John Liu, and my predecessors in arts and sciences, including Catherine Newton, George Langford, and Sam Gorovitz. Thank you for supporting gravitational wave research and, in the words of Peter Solson, for playing the long game. We are truly grateful. Today is an age of discovery. It defines who we are as a Syracuse, as a university, and as a people. The future is only the beginning. Thank you so much.
Thank you, Dean Rouland. At this time, we would like to turn up the lights and ask our panelists to join us on stage for a brief question and answer session. This is your chance to ask this terrific group of physicists more about their latest discovery and why it is so important. So our panelists today are Duncan Brown, the Charles Brightman Endowed Professor of Physics, Stefan Ballmer, Associate Professor of Physics, John Liu, Syracuse University's new Vice President for Research, and alumnus Jason Lord. All right, right, so let's get going. First question is for you, Duncan. Don't mind if I call you Duncan. Today is a very exciting day, so tell us what you and your colleagues have discovered.
So, as Dave described in the movie you just saw, what we've discovered is two city-sized atomic nuclei, these neutron stars, colliding into each other at 1/3 the speed of light. And in the nuclear fire that they produce when they collide into each other, we've seen gold, platinum, the heavy elements that make up the top end of the periodic table, elements essential to life. We've seen the creation of those elements in the universe. So we have a fundamental piece of our knowledge of the universe. Another piece of that jigsaw puzzle has been put into place.
Wonderful, thank you. Stefan, could you share with us what the significance of this discovery might be beyond the world of physics?
Yeah, I guess first and foremost, it really shows that we have a lot to contribute to astrophysics. We've seen this event with gravitational waves, but we were able to pin down where it happened, and we've observed this event now with over 70 observatories, and we're literally learning more than ever before about stellar collisions in a way that was just unprecedented before.
Thank you. Next, John Liu, what a welcome this is for you in your new role as the university's Vice President for Research. So I'm wondering how this would align with your vision of Syracuse University's research portfolio.
Well, thank you. First of all, it's a great pleasure to be here serving as your Vice President for Research for Syracuse University, a world-class research university. This is a great day for the orange and blue family of the Syracuse University. It's really a great day beyond Syracuse because Syracuse, once again, leads the world in physics and beyond physics. So I think this is really inspirational to all the research programs at Syracuse University. I think that will serve as a force to make us to the next level of research progress.
All right, so Jason, can you tell us about your work on the team that contributed to this discovery? How did it happen?
Absolutely. A couple of years ago, I applied for a position at LIGO, and first person I talked to was Duncan Brown. He said, hey, we have a cluster of computers, about 200 of them, that all work on the same problem simultaneously, so we can crunch through the data much faster. I said, Duncan, if we have 200 computers, can we maybe put 20 computers in one box and treat that box like a single computer? Duncan said, yeah, it sounds like a good idea. Go look it up, and he walked away. So my project began of actually figuring out how to stuff a lot of these what we call graphic processing units into one box and treat that box as an extension for a single computer to help us compute more gravitational wave data more efficiently.
Okay, great. Thanks so much. So, Duncan, back to you. A lot of people will be at home watching the webcast, and we've got many members of the audience who may not be in the field of physics. So, might you kindly take a minute to explain what this means to the average person in layman's terms?
So, if you look at human history, for millennia, people have wondered, where do the precious metals come from? Where does gold come from? Where does platinum come from? I'm wearing a platinum wedding ring on my hand right now. In the beginning of the universe creates hydrogen. It doesn't create much else. And for millennia, the universe has been evolving, creating new elements, and eventually creating life. And we are all part of that stardust, that star stuff the universe has created. So what we're learning right now is where we came from, where our planet came from. And hopefully it's going to tell us, where are we going? We can use the discoveries to learn more about the nature of matter. The more we learn about science, the more we can apply those technologies to our everyday lives. So this discovery, while it's an astronomy discovery, and we can look at the sky and say, wow, that's really cool. We've just seen two neutron stars collide into each other, and we've felt the gravitational waves, the ripple in space-time from that collision. The science that we're learning will have impacts on technologies that will affect us today and maybe in 100 years from now in ways that we can't predict.
Terrific. So, Stefan, from a personal standpoint, is there a way to articulate what this discovery means to you and your colleagues?
Well, this is tremendously gratifying. Lots of us have worked on this over many, many decades, pushing this precision measurement to a point where we've just never been before, getting rid of this noise source and that noise source. So the fact that we can now literally listen to stars orbiting around each other, for me, is just one of the greatest things. I'll give you an anecdote. So shortly after this happened, pretty much the same day, I was talking to my 6-year-old. And totally breaking the embargo, I told him about it. I pulled up the sound template of that waveform, and you can listen to that later on. You start hearing the hissing, and then you start this fine chirp of the orbital period shrinking. He listened to it, mesmerized, and the first thing he said is, "Dad, can you make the noise go away?" So the fact that we can touch people's imagination by that and open up literally new window to the universe, a universe that we haven't seen yet in this messenger, is unbelievable to me.
Great. So back to John. You mentioned earlier that this is really big. It's big for the world, it's big for the area of physics, and it's certainly big for Syracuse University. So could you talk a little bit more about how this is going to position the university on the national and global research stage?
Yes, absolutely. If you look into the history of science and technology, it's really stimulating one another, each other. That great discoveries often leads to the great development. It demands for technology further to be developed, and that technology will further then enhance science as discoveries and innovations. So from that perspective, I think this is very big. It's going to demand many new types of technology to emerge that will lead to many different types of research that will have serious implications to our national security and other things. We all have imagined a long time ago how much GPS would have an impact on our life when 30, 40 years ago it was for national security use only. And today, just look at how much impact it has on our daily life. So I think this discovery, no exception, will go to the next level, eventually will lead to very, very serious applications to everybody's normal life. So in that sense, I think very serious, and it certainly will lead to stimulate research at Syracuse University and beyond. Certainly, it leads the entire field of physics that will read it out to all disciplines for greater discoveries and progress.
Great, so thank you. Jason, I mentioned earlier that we're joined today by classes of high school students. I think they're sitting over there and they're very well behaved. And whoever let them out of school this morning to come and hear this historic announcement, hats off to those administrators and teachers. And so I want you to try and speak directly to these young high school students and any other young scholars we might have in the room with us. They're dreaming of becoming a scientist or being part of a future historic discovery. And so what could you say to them to give them hope to stay in these fields, that there's discovery from here on?
Absolutely. I understand it's very easy to get bogged down because we understand the world from both a very macro perspective all the way down to an atomic one. But if we were to compare all the knowledge in existence to an ocean, then what we currently possess is but a drop. There are so many things out there that we still have yet to discover, and it is by far the pinnacle responsibility of students like yourselves to focus on that one goal or just focus on that one curiosity. The cornerstone of scientific discovery lies only two things, and that's curiosity and courage. First, the curiosity to question something that no one has ever questioned before, and the courage to gather a group of individuals to keep working towards that common goal. If you remain curious and remain courageous about being told that something's not going to work, as long as you hold on to the fact that it is, then you'll be successful in this field, that I can promise you.
Wow. That's great inspiration. Thank you so much. So we've come to the end of the scripted questions, but we do have time to answer questions from the audience. So ladies and gentlemen, if you have questions you'd like to ask our panelists, we invite you to step forward, and we have staff with microphones in the front of the auditorium. So please make your way to the microphones. Don't be shy. Maybe we have a question from the students. All right. Go ahead, please.
Hi. So I want to be a sort of chemist or biomedical engineer. I'm just wondering, how does gravitational waves affect matter in any way?
So, do you want to take this stuff?
Oh, sure, I'll take it. So, the basic idea is a distance measurement. We have multiple mirrors in these detectors at large separation, about 4 kilometers apart. And literally all that we're doing is measuring the distance between these mirrors to an extreme precision, like 1/1000th the size of an atomic nucleus. And if you now have a neutron star collision somewhere 40 or 130 million light years away, what you'll find is that that distance between our mirrors starts to fluctuate with the orbital periods of these stars. So that's the measurement we make. It's literally just a ruler. We use light to read that out. And from that measurement, we can then conclude what happened there.
One of the amazing things about this discovery has involved so many different fields of science and engineering. So to build these detectors that Stefan's talking about is an incredible scientific feat to design them and an engineering feat to actually make the detectors work. Keeping these detectors working is a constant battle. They're an engineering marvel to both the civil engineering of building the facilities, the mechanical engineering, all the different pieces that go into it, and the science to develop the lasers, the mirrors, the technologies. And that's just the detection side of things. Then once you get to the astrophysics side of things, we have to understand what we're seeing, what the gravitational waves are telling us, and then on the telescopes, when we've located where on the sky the gravitational waves are coming from, we point telescopes, and then we have to figure out what the light from the telescopes is telling us. And that involves a huge amount of expertise from many, many different fields of science and engineering to make happen.
Great. Another question here.
What was the team's initial reaction when you guys got the proof that it was a gravitational proof of the gravitational wave? What was the initial reaction of everybody? Were you guys in shock? What was it?
So I was in the room, and I don't know if my colleague Mitch Soderberg is here, but Mitch and I were in a meeting to discuss the physics graduate program when I got an email pop up on my computer saying possible binary neutron star candidate event. And Mitch is not a member of the collaboration, so I basically said to Mitch, okay, you need to leave my office right now. I'm sorry, get out. So we started to look at the data, and very quickly we realized this signal is incredibly loud. Black holes make stronger gravitational waves, but the black holes we've seen have been so much further away. By astronomy standards, this signal is nearby. It's 130 million light years away, it's in a distant galaxy, but by our standards, that's pretty close. So the signal was strong, it was loud, we knew right away that it was a binary neutron star system. And my jaw just dropped, I was completely in shock. I didn't think we were gonna see this for another maybe 5 years or so. And then to be able to use LIGO and Virgo to get the sky location, I mean, so you do this every day. You hear a sound, and you turn towards the sound, and you look at where the sound is coming from. And we basically did that. We heard the gravitational waves, we pointed our telescopes towards it, getting everything, getting the signal, getting the gravitational waves, and the visible signal was just incredible. And yes, complete shock was my reaction.
Yes, please go ahead.
So these neutron stars are incredibly dense and thus have all kinds of gravity how is it possible for the heavy elements that get produced this way to be propelled out into the universe and escape the gravitational field?
So when two neutron stars collide into each other, and we had some movies up here earlier, the neutron stars collide into each other and they're spiraling together, so they're not going head on, but even if you collide two cars head on and bits and pieces fly off everywhere, when you collide these two objects into each other at 1/3 the speed of light, material flies off in all different directions. And so you get these tails of material that are thrown off that in the same direction as the stars were orbiting, and so that material then gets, a lot of the material ends up probably in a black hole in the middle, that the material collapses down to a black hole and is lost from our universe. But a ton of material is thrown off as you collide. They're fluffy objects, they're fluid objects, you collide them each other, material gets thrown off, and then over billions of years, or that gets recycled in the galaxy and becomes part of new clouds of gas and dust that then collapse down under gravity to form star systems like ours.
Okay, we have another student question.
Hello. I was wondering what makes this difficult, like the rarity and how they occur, or detecting them?
It's actually both. These type of collisions, neutron stars, are actually more frequent than the ones we've seen before, the black hole mergers, but they're also significantly weaker. So we only see the ones closer, more nearby. So at the current sensitivity of the detector, we see about one of them every year. We've seen one so far after a year, so there's still quite an uncertainty in that number, but it's roughly right. But as you improve the sensitivity of the detector, and we have lots of plans to do that, we'll see these events more and more frequent. So you can make estimates how many of these should happen in the whole universe, and it'll be one every, let's call it 30 seconds or so, that somewhere in the universe this will happen, but most of them are still way too faint for us to see, and we only see the nearby ones.
Next question, Dr. Gorovitz.
It was thrilling to see the Nobel Prize go to those three guys. And of course, if you look at the demographics of Nobel Prize winners over history, it's nearly always guys. And even though the prize went for work that was broadly collaborative, involving hundreds and thousands of people, very few people win the Nobel Prize, and that kind of obscures the extent to which it's collaborative. Now I'm looking up at a bunch of guys who have done some new spectacular work, but there is a focus that we all share, I think, on a more diverse and inclusive science. And so I'm wondering if you can say anything to us about where the women are in the work that you have done and the work that you intend to do. What can you say about that that will be encouraging?
I think one of the things that we're very proud of is in Syracuse is we have a very diverse and inclusive group. I don't know, where are our graduate students? I can't see, the lights are shining in my face.
Yeah, stand up.
So stand up, wave. So I can see Shomi, who's working on she's working on the physics of what happens when these neutron stars collide into each other and trying to learn about the structure of matter. Shweta, who stood next to her, she's working on black hole collisions and trying to figure out understanding what black hole collisions can tell us about the nature of gravity. I think I can see Hannah behind, who is working on with Stefan on the next generation of gravitational wave detectors. Jax is working on developing detectors. Derek is working on understanding the noises we see in the current generation of detectors. I think I see Daniel at the back. I have bright lights shining in my face, so sorry if I can't see anyone, who's also working on building detectors. So this is the team that makes it happen just locally in Syracuse. So we have a really great team of people here, and also nationally, Gabby Gonzalez was the spokesperson of the LIGO Scientific Collaboration when the first discoveries were made. She's a Syracuse alum. So we have a team that's really dedicated to making this happen, and I'm really proud of the group here and everything they've done.
Yes.
Hello. Can you hear me? How you doing? So you found gold coming out of these neutron stars. What about, there's a lot of elements heavier than gold out there. Are there any thoughts to where they come from? Do we already know where they come from? And also, one more question just on top of that. Radioactive elements, do we spot any of those coming out of neutron stars?
So we've emphasized gold because it's an element that people are familiar with and everybody cares about. Given that I know you're a physicist, I'll say we've seen the R process group elements. So basically, when stars burn hydrogen, they can burn hydrogen into elements up to iron. So the bottom half of the periodic table between hydrogen and iron is made from fusing elements together. Above that, it takes energy to make the heavier elements. And some of those heavy elements are made in supernova explosions, but it doesn't make iridium and gold and platinum and selenium and other heavy R-process elements that are essential for life on Earth. That's what you're seeing in the neutron star merger. So the glow that we're seeing of the neutron star merger is the radioactive decay of these, about half the elements heavier than iron, being forged in the radioactive decay of the tails of the neutron star. So yes, we see more than just gold, and yes, we see radioactive elements.
I think we have time for a couple more questions of people standing at the left.
Hi. So in the fact sheet that was distributed out to us, and everybody here coming in, mentions something about a glitch in data on the 17th that caused some problems with being able to get everybody to turn and look at the source. And it says that some scientists and students here played a role in fixing that. And I'm wondering if you might be able to sort of like tell the story and help us to understand the role that some of you might have played and the role that Syracuse played there generally.
Yeah, maybe I'll start it off explaining what that glitch was, and then I'll hand it over to Duncan. So these detectors don't always work perfectly. Every now and then something goes wrong. There is a little timing glitch, some frequency counter misses a tick, or you have some dust falling through the laser beam or something of that sort. And part of our job is to make sure that all these glitches are well accounted for and don't mimic any gravitational waves. Now in this particular one, the Hanford data was very clean and the signal was first spotted there. The Livingston data was actually automatically flagged and not used. And only after we've seen the Hanford signal, we went back to the Livingston signal and saw this huge transient. But left and right of that transient, we saw the signal of the neutron star binary still present in the data. So the effort then was to clean up that one piece of data, and I'll hand it to Duncan at that point.
Yeah, so the key thing to get the optical signature is to figure out where on the sky it is. The sky is a big place, and telescopes have very, very small fields of view, so you need to know exactly where to look. And with the glitch in the Livingston detector, the Hanford detector told us, it's about there, which is pretty much useless for astronomers who want to follow it up. So what we had to do was, and Peter Solson and Stefan and myself have trained a group of students who are, some of whom are still in Syracuse and some have gone on to other places now, who are experts in figuring out what these glitches are, removing them from the data, and then we rapidly reanalyzed the data, and that was something that a lot of Syracuse people were heavily involved in. Former graduate student Alex Nitz was the person who did the reanalysis. We did that quickly enough to get a sky map before the source set below the horizon. So the limiting factor in getting telescopes on the source was it being dark, not anything that was a problem with the LIGO or Virgo detectors or anything we could do, because Syracuse students and current and former students and scientists have worked quickly to make that happen. And so that's something, again, I'm really proud of the Syracuse contribution, that we got that sky localization quickly because the team reacted quickly.
Okay, I think we have time for one last question. Yes, Joyce.
Hi, I have a question for Jason. Yes, hello. Class of 2017. So my question is, how did being a part of this transformative team impact your student experience at SU? And how can other SU students be involved in such research efforts?
my social life was non-existent. No, more than that, it was great. After the first detection, we knew that we'd be famous for 3, maybe 4 hours, and we capitalized on that. So we had the front page of Syracuse.edu. It was all of our faces. So of course I had to tell everyone, go to the web page because we're now celebrities. But it was great. What I learned working with LIGO for the last 3 years is much more than I've learned in the last 10 on my own. Real world experience in the lab and actually seeing how science is really done and how it is just a very big, large process of trial and error, continuous trial and error, and mostly ending in failure, was one of what I would consider the most important lessons for not only myself, but I think any student involved in any sort of research. To understand that most of your experiments are going to fail, and knowing that there's a good chance that most of the future ones will fail as well, and still being inspired enough to continue, I think is one of the most prominent gifts that I ever could have got working with a group like this.
Great. Well, one last question, okay?
So hi.
Hello.
Okay, good. Hello. Nothing is lost, nothing is gained. That is one of Avogadro's law. And I'm just wondering, when these neutron stars collide, what happens to the energy that they emit? And when you detect those gravitational waves, if they are like radiations, do they also affect human skin? Just wondering.
So the energy of this neutron star collision is what powers the light that we see, the flash of gamma rays that we see, the radioactive decay, the creation of new elements. So that energy goes into a ripple in space-time of gravitational waves that comes out, and the light and the energy needed to create the new elements. So the energy is conserved. You're completely correct that the energy is conserved, the matter is conserved. It just gets transformed from one form of energy into another form of energy, and one form of matter into another form of matter. So, Stefan, do you want to?
Yeah, I mean, most of the energy is actually in form of gravitational radiation, but you don't have to worry about that affecting you in any way. The interaction with matter is so minuscule. That's in fact what makes it so hard to see them in the first place. But that's also what makes them so beautiful and promising for the future, because unlike anything else, the gravitational wave will allow you to see further back in time, at a time where the universe was completely intransparent to light. So there is lots to be discovered, and since we have a lot of young people here, don't think everything is done yet. It's quite the opposite. There is a huge amount of work to be done and new things to be discovered.
And there's one more. This is absolutely the last question.
I'm very honored, Professor. Thank you very much. So, what spatial, tactile, or linguistic conceptual frameworks would you use to help make these beautiful discoveries accessible to people who are blind and deaf? So if, for example, a sign language interpreter was going to express a translation of this conceptual framework without sound, or someone was going to access it without vision, what ways would you help make sure that everyone could access that beautiful news?
I think so. Gravitational waves are vibrations in the fabric of space-time, and so one of the things you can do is you can put a transducer and you can literally feel them. So you can feel the vibrations of the gravitational waves, because this is a rippling of space-time. This is space itself being stretched and squeezed. So this isn't one of the ways we can conceptualize this is as sound. We can transduce it into sound, but these are literally vibrations in space itself. And so you can transduce those vibrations as physical vibrations that you can amplify the vibrations and you can manifest them that way. So that's one way that people can experience this without audio and sound.
Wonderful. So this concludes our program. If you have more questions, I've been told that the LIGO students will remain in the auditorium and they'd be more than happy to share answers with you at the resource table. I'd like to thank all of our panelists. I'd like to thank Chancellor Syverud and Dean Rouland. And finally, I'd like to thank all of you for joining us today to celebrate history in the making. I invite you to join us for a brief reception here in the auditorium. We're not giving away any gold or platinum, but there are some amazing cookies with the elements of the periodic table on them that you can take away as a remembrance of this amazing historic event. So once again, I'd like to take one last opportunity to thank our great team members and to celebrate together this exciting breakthrough discovery. Have a wonderful day.